Okay, it's almost time is coming. Hello, everyone. Good afternoon, good morning, and good evening. My name is Katsutoshi Toyama. I am from Tokyo Institute of Technology. I will be the chairperson of this session. Okay. This session is music information retrieval and modeling. A total of 6 presentations will be given. The time slot for each presentation is 25 minutes. 18 minutes for the presentation, and the remaining 7 minutes is for Q&A session. Presenters, please manage the presentation time by yourself. And presenters, please turn on the camera during the presentation, if possible, so that your face can be seen. Audience, please turn off your camera and microphone, except when asking questions. And if you want to ask a question during the Q&A session, please use the raise the hand button. Or post your question on the chat of Zoom. I will name the person who raises his or her hand. And the named person should turn on the microphone and the camera if possible, and start asking questions. You can post questions to the chat box either during the presentation or during the Q&A session. I will pick up the posted question and ask it to the presenters. And after all the presentations are finished, there will be a 20-minute post-session discussion period for those who want to ask questions or greet the presenters. Presenters, please move to the breakout room corresponding to your presentation number and stay there during the discussion time. Audience members are free to move the breakout room of the presenters they want to talk to. Okay, so the first presentation, the title is Lyric Document Embeddings for Music Tagging. And the presenter is Matt McVicar. Okay. So if you are ready, please start.
Hi, do you hear me okay?
Yes.
Great. And do you see the presentation? Yes? Okay. Great. Great. Hi, everyone, and thanks for the introduction. So I'm here to talk to you about creating lyric embeddings at scale for use in music tagging. This work was conducted in collaboration with Bruno Di Giorgi, Baris, Dundar, and Matthias, Mauch. And we're part of Apple Media Products and part of the music machine learning team. So to begin with, here's an overview of what I'll be discussing today. Let's begin with discussing the task. The usual setting for tagging in MIR is to attempt to assign semantic tags to a song based on audio content. Typically, each tagging task, such as genre identification, explicit content identification, is handled separately. Here we see audio inputs and 4 different taggers used to identify genre, mood, explicit content, and flagged categories such as spoken word. In this work, we attempt to build a single tagging model which is able to classify a number of tagging domains based on the lyrics to a song alone. In this diagram, we show a lyric string as an input and a single tagger which is able to classify all 4 domains simultaneously. So a good question is, why would we want to do this? Well, there have been recent advancements in natural language processing, with new models frequently being published at top-tier machine learning conferences. However, it's not clear if these gains carry over to the MIR domain. And from an Apple Music perspective, it would be useful for us if we had a flexible, general purpose lyric representation for use in other pipelines that we use in our team. So in this sense, having embeddings which are able to effectively represent a huge range of tags seems like a good objective, because we think it will lead to general purpose embeddings. Next, I'll talk about some of the challenges of this work and our contributions. In terms of challenges, there is a wealth of choice of modern natural language processing models, and it's not clear which, if any, are best for lyric processing, or even if they outperform simpler models. Some authors recommend warm starting the training from a larger corpus than you have access to, whereas others do not. Finally, some authors simply average word embeddings to achieve a document level vector, while others use sophisticated sequence models. And it's unclear to us which is best for music tagging. So our main contributions in this work are as follows. First, we qualitatively investigate different methods for producing word level lyric embeddings. Next, we try various techniques for aggregating these word embeddings to a document representation. The evaluation of these models is conducted in a new multi-tag, multi-label scenario and runs at the scale of tens of millions of tracks. Now let's talk about the overview of our pipeline. Overall, our pipeline looks like this. It's a little complicated, but let's go through it step by step. We begin with raw lyric strings and pre-process them by tokenizing and removing uncommon words and things like this. I'll go into more detail about this later. We then compute different representations of the words or tokens in a song. So we begin with random embeddings as a baseline, and also compute word indicator vectors, which are ready to be summed up over the document to form bag of words representations, for example. Finally, we compute word-to-vec embeddings from our corpus. Now, we need to gather the word vectors into a document representation. We do this in an either supervised or unsupervised way. For the unsupervised approaches, we simply computed the sum or the average of the word vectors, and also tried TF-IDF reweighting. We also tried doc2vec, which is an extension of word2vec, which uses paragraph indices to come up with a document representation. In terms of supervised methods for computing document representations, we tried two sequence models, an LSTM and an attention-based model. To train the sequence parameters of these models, we need a target in order to optimize. Not wanting to use a label which would confound our tagging experiments, we used the artist identifier here. Whichever technique we used, we've then arrived at a single vector representing the lyrics of the song. We then tested these embeddings in a challenging tagging task. Let me take you through our tagging model. So we begin with our trained frozen embeddings representing the lyrics to a song. We then pass these through a series of dense layers, which branch off to one set of dense layers per tagging task. Note that this part of the chip pipeline is trained separately to the document embeddings, as it is used for evaluation only. To recap, we investigated the following simple approaches. First, random embeddings with dimensionality 128. Next, bag of words and TF-IDF models. We also explored a range of different embedding dimensions here. We then trained a word-to-vec model from scratch on our data, and also tried warm starting the training from the very large Google News 300 model, which is trained on approximately 100 billion tokens. In all of these experiments, we used simple averaging or summation to calculate a document level representation. In our next experiments, we tried 3 methods of summarizing word embeddings beyond simple averaging. First, we tried doc2vec, a model which trains with a similar objective to word2vec, but with additional input representing paragraph indices. Next, we tried 2 sequence models, an LSTM and an attention-based model. In both these models, we ran the sequence model over the sequence of word embeddings and used the artist ID as the target, as discussed previously. We were interested to see that actually in our experiments, the accuracy of this artist identification task was reasonably high at around 0.6. Now let's take a look at the data sets we used in our experiments, starting with the raw lyrics data. So we began with around 20 million tracks, which had primary language as English. We tokenized these in the Python GenSim package and truncated the sequence length to 512 tokens for scalability reasons. This saved us an order of magnitude of sequence length, so around 8,000 to 500, yet only affected around 4% of the documents. After all this processing, our data still consisted of nearly 4 billion tokens. In terms of the tagging data we used for evaluation, we worked with 8 diverse data sets. Here I'm showing these as rows in the table. The columns represent various summary statistics, which are approximately rounded. There's a lot of information here, so obviously I won't go into too much detail, but I'll show you a few interesting points. First, worth highlighting is that the number of distinct labels per dataset varies from 2, i.e. binary classification, for things like explicit content identification, up to around 500 distinct labels for some of the genre tasks. In several datasets, there is more than 1 tag per track, meaning it's a multi-label dataset. There's also a wide range of track coverage, from around 40,000 tracks to 500,000. Note that these datasets are used only for evaluation. Our document embeddings are trained on the full set of 17 million songs. Nevertheless, we will need to balance this discrepancy of track coverage carefully when evaluating the models. I'll discuss our training procedure next. For the simpler methods, the training procedure is quite straightforward. For the baseline models, we trimmed any word which appeared in more than 90% of the documents, and then kept the D most common remaining words. And we did this for D equals 128, 256, and 512. We were naturally interested in using PCA to come up with vocabulary in a more principled way, but actually couldn't get this algorithm to scale to our datasets. In the word2vec models, we kept all words which appeared at least 5 times. When warm starting the training, we set the initial vector to be the pre-trained vector if possible, i.e. if it appeared in both datasets. Otherwise, we set it to be random as usual. We trained all the word2vec models for 5 epochs. The training procedure for the tagging part of the model is a bit more sophisticated. So recall that we'll take as input a single embedding representing the song lyrics, pass it through some dense layers before branching to dense layers per tagging task. For each task, we compute the categorical cross entropy because remember that some of these tasks are multi-label. And then the loss for a song is then a sum of these individual task losses weighted by the number of tracks in the dataset for that task. And we need to have a little indicator function here to say that if a track has no labels for a given task, the loss is set to 0 for that task. Finally, in terms of training, we compute mean average precision at each epoch and stop training when this value plateaus on the validation set. We tuned hyperparameters using Bayesian hyperparameter optimization and sweeping over the parameters you see here. The objective of this model was the best mean average precision on the validation set. And we ran 20 trials concurrently, and in total 100 trials were conducted for each model. Model training time varied significantly, but took approximately a few days for each trial. Okay, now let's see some results. We begin with word level embeddings, where we simply average word embeddings to attain a document vector. Here I'm showing mean average precision on the y-axis and various model types on the x-axis. The results are grouped by task. Note that there's a wide range of performances due to the variety in the number of classes in each task. For example, the explicit task is binary, so all the scores are at least 0.5. However, genre 1, for example, has nearly 500 distinct labels, so all the results are lower in magnitude. Worth noting as well is here I'm only showing 512 dimensional vectors, as these models always performed best. The red bars show word2vec trained from our own dataset without any pre-training and achieve the best results in almost all tasks. This is actually one of our main findings from this work. We therefore chose word2vec 512 dimensional vectors as our best word embeddings and set out to discover if we can improve tagging accuracy with more sophisticated aggregation methods. Here, we trialed 4 methods for aggregating word2vec vectors into a document embedding: averaging, Dr.vec, and 2 sequence models, LSTM and the attention-based model. The experimental setup, metrics, and data sets all remain exactly the same. Here we see that the attention-based models in the red bars sometimes outperform simple averaging of vectors, shown in blue, although in many datasets the order is reversed. So it's unclear to us why the powerful sequence models do not yield higher scores. One reason could be that we have sufficient data to train excellent word level embeddings, such that further refinements are simply hard to realize. With this in mind, we tried limiting our training data to see the effect it had on performance. Here, I'm showing our chosen model, averaging of 512 the word2vec vectors, with various training sample percentages. So the y-axis is again mean average precision, but this time the x-axis is the epoch number of the best performing trial. We limited the training data sets logarithmically from 100%, which represents around 17 million songs, all the way down to 0.001%, which is around 170 songs. As expected, as the training set decreases, the performance metric goes down, but actually it decays quite gracefully. In particular, it seems that by limiting to 1% of the data, which is around 170,000 songs, so that's the green line, you can see the peak performance is actually around 80% of the best performance we get from using all the data. Finally, let's conclude the work. So our main finding is that it is hard to surpass the performance of relatively simple models trained on in-house data. We saw some small improvements through more sophisticated sequence modeling, although the results were not that conclusive. Experiments on sample data showed that increasing the training set size beyond 1 million songs did not significantly improve tagging performance. Thanks very much for listening. I'm happy to take questions.
Okay, Thank you for your presentation. Okay, we will go to Q&A session. So if you have question, please raise your hand or put the question into the chat box. Okay, so the question from me. So when comparing a song that contains a lot of words and phrases used only in lyrics, especially in lyrics and songs, and a song that contains a lot of general words and phrases, can the proposed method, proposal model handle both of them equally well?
Let me repeat the question so I check I understand. Are you asking about the difference between general use of language in lyrics and very specific?
Yeah, so I can quickly think a specific example of English songs. But...
yes, I think so. So the idea behind training on a large corpus is that we get exposure to a lot of different types of language used in lyrics. So I had the same concern as you when I was doing these experiments, which is one of the reasons we tried pre-training. So we tried, warm starting the training, trained on the general purpose language and fine-tuning on lyrics. But as I showed here, it didn't really seem to help. It seems that if you have enough data, then you can train a model from scratch just on lyrics data alone, and it will understand the right properties of lyric language alone.
Okay, thank you. For any other questions? Okay, so one more question from me. Okay, so please explain the difference. So sorry, this is this. So you your training tagging data sets contains some kinds of genre 1, genre 2, genre 3, genre 4. So please explain the difference of them again.
Sure. So one of the benefits of working in a large company is we have access to lots of different data sources. So we have, for example, when a record label uploads a song to Apple Music, that will get assigned a genre tag. But sometimes these aren't very accurate, or they are they're quite broad, so it might just be rock or something. So we have various sources of data from the record labels, but also from things like if songs appear many times in a playlist which has a title similar to heavy rock, something very specific, I don't know, heavy rock for driving or something, then we are able to make kind of ground truth data sets from those sources as well. So the short answer is we have lots of different sources of these data, and they vary a lot, as I showed. So some of them have maybe just 20 different classes. Some of them are up to 500. So it varies quite a bit.
Thank you. So, any other questions? We can accept a short one. No? Okay, so its time is coming. Thank you for your presentation.
Thank you very much.
Okay, we will go to next presentation. The title of the presentation is Oktoechos classification in liturgical. I cannot pronounce it correctly. Liturgical music using musical texture features. The presenter is Varsha Shiburaj. Okay, so if you are ready to start, so please share the link.
Yeah, can you see my screen?
Yes, perfect. Okay, please start.
Hi everyone, my name is Varsha Shiburaj and I'll be presenting on the paper of Oktoechos classification in liturgical music using musical texture features, which is co-authored by Dr. Rajeev Rajan, Amlu Joshy and myself from College of Engineering, Trivandrum, India. So our paper is basically based on the classification of Syrian traditional music. It is classified into 8 tunes called Oktoechos. The liturgical hymns are sung in 8 modes or 8 colors. In this paper, automatic Oktoechos genre classification is addressed using musical texture features, eye vectors, and MEL spectrograms through deep learning strategies. Although there has been significant work in the musical genre classification, the proposed task of liturgical music genre classification is first of its kind. The vast diversity of forms, styles, and functions in the music used for worship makes it challenging to categorize liturgical music. So that is the difference with the normal music classification. The aim of the work is to explore the ability of LSTM networks to capture long-range dependency in learning temporal patterns. So for our database, we used a newly created corpus of liturgical music in Malayalam, which contained 384 audio files, which was equally divided into 8 classes, with 8 classes containing 48 songs each, with the duration of 25 to 45 seconds per file. It was sung by 15 professional singers in the age group of 12 to 50. And the recording was recorded at the frequency of 44.1 kilohertz. And the data set was then split into 60% of the file used for the training data set, 10% of the files used for the validation data set, and the rest of the 30% was used for testing. So for feature extraction, the timbral features consisted of MFCC features, that is MEL frequency septal features, and low-level timbral feature set. The low-level timbral feature set had spectral centroid, spectral roll-off, spectral flux, and spectral entropy. So besides all of these features, we also had tempo, pulse clarity, and event density, which made the rhythmic features. Then we used eye vectors to classify because it can be used as a performance comparison for the above MTF features. We also use the visual representation of audio files, which is spectrograms. So this was also used for a performance comparison. And for the experimental setup, we used MFCC features. So that is of 13 dimensions. We took its delta and delta features, so which makes it 39 dimensions in total. So 39 dimensions with the timbral features of 4 dimensions and rhythmic features of 3 dimensions made a 46 dimensional MTF feature. It had a frame width of 40 millisecond and hope size of 10 millisecond. The I-vector experimental phase had 100-dimensional I-vectors, which were computed using 128 mixture GMM from the MFCC using Ali's toolkit. Then, with all of these configurations, we computed the precision, recall, and F1 measure scale as a basic evaluation metrics for all of these configurations. So these were the results that we got using different configurations. We used 5 different configurations. The first one is MTF features with SVM neural network, which is 42.65 accuracy. And then the second one was MTF with DNN neural network, which gave us an accuracy of 48.70. Then I-vectors with DNN, which gave us an accuracy of 50. So these deep learning schemes and SVM are implemented using Keras, TensorFlow, and libSVM respectively. DNN was based on 6 hidden layer network in successive layers with dropout of 5. The network was trained in a batch of 32 and for 150 epochs by Adamax optimization algorithm. ReLU and Softmax has been used for hidden and output layers respectively. And for the fourth configuration, we used MEL spectrogram with CNN, which gave us an accuracy of 52.60. So the proposed CNN had 6 convolution networks layers followed by max pooling. We used filters with very small 3x3 receptive fields with fixed stride of 1 and increase the number of filters for the layers by a factor of 2 after every layer. Global max pooling is adopted in the final max pooling layer, which is then fully fed into the fully connected layer. The training was done with 100 epochs by optimizing the categorical cross entropy between predictions and targets using Adam optimizer with a learning rate of 0.001. Then lastly, for the LSTM network, we used MTF features, and that's how we got the maximum accuracy of 83.76. So the LSTM network was effectively utilized to track the temporal pattern embedded in the modes of music. It had a 2-layer network of 64 hidden units and 1024 hidden units. It had also dropout layers of 0.25 each. So this slide shows the class-wise performance of each of the following configurations. So we can see the green bar representing the LSTM clearly outperforms the other approaches with a significant margin. This is the precision, recall, and F1 measures for each of these configurations. So it is reasonable to say that the time pattern capturing the scheme is needed in order to recover more relevant information from the temporal embedded music traits, which is LSTM. So LSTM utilized the MTF features to capture song dynamics effectively to perform the Oktoechos classification of 8 classes. The possible cause of the low value of accuracy in I-vectors may be potentially due to the inability to capture the rhythmic temporal dynamics well within the given framework. Besides that, the aggregation of musical texture features to track level might have been deteriorated the performance. So for the CNN network also, the results improved as the number of layers increased up to 6, but then it got saturated due to overfitting. It is due to the fact that as it increases, the model depth grows. So the proposed experiment validates the claim that the temporal information has effectively been learned by the MTF LSTM framework. The experimental insights show that the performance of the system depends on the temporal architecture, which is basically designed by considering the musical domain knowledge. So these are the normalized confusion metrics of MTF LSTM and the TSNE plot. So this is a class-wise confusion metric. So we can see that all of these classes have accuracy of greater than 70%, and the class 5 and 7 has accuracy 90%. This is the normalized confusion metrics. So from the TSNE plot, we can see that there is good clustering and a general separation of different classes. It is important to note that effectiveness of LSTM for the proposed task without using any modeling or data augmentation, unlike what we used in iVector or CNN. So it's even with the data augmentation, it would be a little more accurate. So in conclusion, Oktoechos classification is addressed in this paper with MTF LSTM framework, giving an average classification accuracy of 83.76%. Since the Greek liturgy and the Gregorian chant also share the similar musical traits with Syrian tradition, the musicology insights observed can be can be potentially be applied to those traditions as well. These are the references that we used in our paper, and that's it. Thank you.
Yes, thank you for your presentation. So we will move to the Q&A session. So please raise your hand if you have a question. Write the question into the chat box. Okay, so the question from me. So could you play back or could you play back a few examples of music from each class? So because many participants can't necessarily imagine what each class is like.
So right now I did this experiment during my undergrad in India, but then right now I'm doing my master's in UK. I don't have any of these experimental setups, but then it's really different than the usual music genre classification. I don't think even I have played those audios, but then I couldn't understand the difference between each of these classes, because it's like very close to each other, very similar to each other. Unless you understand music very well, I don't think that you would understand it. Also, it is a kind of worship songs. So it is traditional songs. So it is very similar. It would have a similar tune also to it. I would have played it if I had it with me. I'm really sorry.
Okay, so for example, what elements do these classes correspond to? Let's say, so for example, Western music, tone or genre or instrumentation or so on.
Can you repeat the question? I did not clearly understand.
So what kind of elements the classes correspond to?
What kind of?
What kinds of elements? For example, the chord or genres or instruments and so on.
I cannot quite get your question. I'm really sorry. If you could type it, maybe. If you can type the question, maybe I can understand.
So actually, I cannot imagine how difficult the problem is. How difficult the classification problem.
The problem.
Yes.
So
how difficult or how easy the classification problem is.
So yeah, as I showed you the classification, it's like the 8 classes are really similar to each other. So as we can see with DNN networks, we have used MTF features, the same MTF features that we gave to the LSTM network. And also with CNN, we have used spectrograms and also I vectors with DNN. With each of these, the classification accuracy that we got is quite low compared to the LSTM ones. It is because we actually got the long range dependency with LSTM. All of the other neural networks don't have that criteria of classification. So it's really difficult if you don't have that. So even with human ears, if I could not like identify the difference between all of these classes. But then if you hear a music genre like hip hop or jazz, you could easily identify the difference. But then I don't think if you don't know those music like traditional music, I don't understand. I don't think one can understand it easily.
Okay, thank you. So, any other questions? Okay, so the one more question for me. So, do you have a plan to publish or release the created dataset?
Plan to?
Do you have a plan to release or publish the created dataset?
Yeah, we can
Really?
actually, yeah.
Oh, okay.
So we'll finally like compile all of this. We have to do some more data augmentation, so we can actually publish the data set.
Okay. So any other questions? Okay, so actually we have several minutes for Q&A session, so but we will move to the next presentation. Okay, thank you.
Thank you. Thank you so much.
Okay, next presentation. The title is Modeling Moral Traits with Music Listening, Preferences and Demographics. And the presenter is Vjosa Preniqi. Is it okay?
You got it wrong. You got it right, sorry.
Yes.
Okay, perfect.
So please share your screen.
Okay. Can you see my screen?
Yes, perfect.
Just
Screen start.
put this. I'll just bring this, or yeah, I can hide it somewhere. Okay. Just trying to hide this. Anyhow, hello everyone. I am Vjosa Preniqi, PhD student at Queen Mary University of London. Today I'm going to talk about modeling moral values with music listening preferences and demographics. This study has been conducted in collaboration with Kyriaki Kalimeri from EASY Foundation and Charalampos Saitis from Queen Mary University of London. So music has always been integral part in our daily lives. We use music to express our emotions, feelings, and ideas. Music influences a wide range of human behaviors such as thinking, reasoning, creativity, and mental flexibility. Many researchers in the past have tackled the association between music and personality traits using a range of data sets such as surveys, digital footprints, music streaming, and so on. Whereas in this project, we analyze music and a more complex psychological dimension, such as moral values. Our main goal is to understand and be able to predict moral values based on music preferences. We tackle moral values because they are very important for our judgments. Also, they have a great effect in the decision-making process. They influence attitudes and behaviors towards controversial and complex topics such as climate change, vaccination, poverty, ideological extremism, and so on. Therefore, by modeling values and music, we can further help in shaping cultural variations, understanding users' well-being, understanding political and social trends, and so on. In this study, we use moral foundation theory, which was presented initially by Haid and Joseph in 2004. This model includes 5 major foundations and 2 super foundations. So we have individualizing, which includes care and fairness. And the super foundation supports the idea that basic structures of the society are individuals, and it focuses on their protection, equal and fair treatment. Whereas the second superclass or super foundation is called binding, and it includes purity, authority, and loyalty. This super foundation represents the values based on respect, leadership, and tradition. So, understanding the link between music and value can further help in other studies, for example, in improving recommendation systems with personalized content, also can help in designing better well-being and health applications, increasing engagement to communication campaigns, and in general, enhance the data-driven decision-making in fields such as psychology, musicology, social sciences, entertainment, and so on. For this study, we have employed a third-party marketing survey administered online. Initially, this survey had 2,000 participants, but after cleaning and pre-processing, we remained with 1,062 participants from 12 different regions in Canada. We also assessed the representativity of the data with actual music behaviors from a music listening histories data set, or MLHD. In the survey, participants completed questions regarding their music preferences, moral foundations, and demographics, such as age, gender, education, political views, and so on. In the survey, also, users scored the preferences using 13 genres. And in order to justify these 13 music genres, we explored a subsample of music logs from Canadian listeners in the MLHD with a similar age and gender distribution as in our survey. The MLHD, on the other hand, is a very big data set which contains music behaviors, or better to say, 27 billions of music logs from Last.fm, which is a music web application. MLHD gathers the data from 2003 until 2014. And the users who have been part of this data set come from 239 different countries. From the MLHD logs, we have been able to extract artist music genres using the music brains identifiers, which are part of MLHD logs. So we did that in order to compare the most listened to genres in actual music behaviors with pre-assigned genres in the survey. So based on this experiment here, I have visualized top 10 most preferred genres from users in Canada, extracted from 2 different data sets. So basically from the survey that we use as a major experiment in this study, and MLHD, which represent musical behaviors. And here we see that slightly similar genre trends have been encountered in both data sets. After analysis with genres from both data sets, we conducted correlation analysis on our survey data set in order to find the relationship between moral values and different music genres. So here we have presented only the most significant Spearman correlations between these music genres and moral foundations. So as you can see, Christian and country music are positively correlated with moral foundations of binding, such as purity, authority, and loyalty. Whereas on the other side, we see that punk is negatively correlated with these moral values. In general, correlation analysis helps us to kind of anticipate how important each music genre or each music feature is for understanding moral values and their variability. Next, we predicted whether a respondent belonged to a high or low end of each moral foundation with a threshold at a median value. So this is a data binding experiment that we have done because original values of moral foundations were actually continuous scores or continuous values, whereas here we classified in a binary manner. So we opted for a gradient boosted algorithm, or XGBoost, for the prediction models. Also, we used support vector machine and random forest, but they did not outperform the XGBoost model. And that's why we present here only the XGBoost model. Then we applied for each model 5-fold cross-validated setting, and for the evaluation, we used area under receiver, or AUROC score. After that, we considered 3 types of scenarios for the prediction models. In the first scenario, we used 13 music genres. In the second scenario, we used 5 latent factors, and in the third scenario, we extracted a music feature called Generalist, Specialist, or GC score. In the second scenario, we applied principal axis factoring with Promax rotation on 13 music genres. And we obtained a 5-factor solution, which accounted 67% of the total data variance. From these factors, we see quiet, structured groups or clusters of music. For example, in the first factor, we see jazz, classical, Latin music, which are more complex genres and sophisticated as well. Whereas in factor 2, we see genres which are classified as more intense and loud and non-mainstream genres, such as heavy metal, hip hop, rap, punk music, And in the third factor, we see pop, and R&B, which are more danceable and upbeat types of genre. And then we have in the fourth factor, we have Christian, country, and folk, which are more traditional or conventional genres. Whereas in the fifth factor, we have alternative pop rock and rock music as more popular music than maybe the heavy metal, for example, which is in factor 2, less intense and less louder. I am explaining this because usually from previous studies, you see that in factor analysis, rock music, alternative pop rock, and heavy metal tend to fall into the same group, whereas here we see as separated groups. And we thought that this might be due to the fact that rock and alternative are more mainstream, are more popular music, whereas heavy metal and punk music, for example, have more non-mainstream features and in general are louder music. As a third scenario, we use an adapted version of generalist specialist score, which was inspired from work that has been done in Spotify for analyzing music diversity consumption. So here, the projection of 13 music genres into 5-factor loadings was considered as genre vector in representation of preference space. The GC score actually measures the cosine similarity between genre vector and the preference weighted average of users' genre vectors. So this is a diversity music feature. So using these scenarios, as I mentioned before, 13 music genres, 5 Latin factors, and GC score were used as a separate set to predict moral values and moral superfoundations. So from the results, we see that 5 factors and GC score, which accounted for only part of data variance, did not manage to outperform the explicit information of music preferences, or better to say, did not perform better than 13 music genres. And this might be due to the fact that, of course, 13 music genres accounted for overall data variance. And then besides 13 music genres, we advanced our models even more by adding demographic information such as age, gender, education, political views. And then the results showed that the more information that we give for the users, the better models we end up with. But however, the improvements were not very significant, and this shows the importance of music preferences alone in explaining the variability of moral foundations. Here, we utilized SHAP analysis in order to extract each feature importance for predicting moral values. So in the picture, you see moral values of individualizing and bindings and the most important or impactful features. For individualizing, the most impactful feature was Christian music, followed by age, then gender, education level, and so on. And then for binding, we have age as the most impactful feature, then Christian, education level, and so on. Then in order to ensure that the most predictive features emerged from the classification process are indeed descriptive of moral foundations, we conducted regression analysis. And as I said, we did data binding in classification model, whereas in the regression model, we use original scores for moral values. For this experiment, we use the same experimental design, whereas for model evaluation, we use mean absolute error. Based on the results from the regression analysis, we see that yet Christian music genre has been the most impactful for both binding and individualizing, followed by age, which was also really important predictor. So this kind of shows us that in classification and in regression tasks, we have similar importance for the features such as Christian music, age, education level, gender, and so on. To summarize with this project, using an ad hoc survey, we predicted moral values based on 13 music genres, and the best accuracy was achieved for binding foundations up to 72.72 AU rock score, while the most impactful features were Christian music and age. We also quantified music diversity using features such as GC score based on 5-factor loadings. Moral foundations, as it's already known, are quite strongly linked with political views. Despite that, music features were more predictive than political leanings in this case. Also, we figured out that people naturally express their morals, and through the music and genres they listen to. People instinctively also categorize objects, symbols, but also other people while creating the notion of social identity. Our findings suggest that musical preferences are quite informative of deeper psychological attributes. However, there is still space for improvement. For example, we noticed that care and fairness foundations were harder to predict. To this end, we aim to explore musical content analysis, for example, incorporating linguistic cues and moral balance scores on lyrics to further improve the performance. Also, in the future, we aim to dive deeper into relationship between music and moral values by using music listening behaviors from actual music streaming platforms and digital footprints, for example, analyzing music preferences from music likes outside the lab settings and over a period of time. Here I have depicted only some of the main references. And I hope I was clear with this presentation. And thank you very much for your attention. If you have any question, you can ask me, or I'll be here for a while. You can drop me a message or an email as well. Thank you.
Thank you for your presentation. So we will move to the Q&A session. So please raise your hand, press the raise your hand button if you have a question, or write your question into the chat box. Okay, so question from me. So in this study, so you have analyzed the relationship between musical genres and moral.
Mm-hmm.
Okay, so is it possible to analyze more precise musical genre, or for example the musical tags, the relationship between musical tags and moral? Is it possible?
Yeah, so basically, when analyzing such complex psychological dimensions, there is nothing such as right or wrong. However, we try to kind of see, based on the results from the user scores in moral values based on the models, psychological models, then we just try to see how well the model could predict the actual scores of moral values. However, on top of that, we are more interested to see what is the exact relationship of music and morality in general, because this topic has been more discussed using textual contents, for example. However, it hasn't been analyzed a lot in terms of music genres or music listening preferences. And as I said before, there are more studies that have analyzed, for example, personality traits using Big Five models with music. However, this is a more advanced and more complex model, psychological model, because it kind of captures not only individual interests, but also it can detect the societal interests, because moral values are very influenced by the communities where we are brought up, the religion, beliefs that our community holds as well. So that's why we were trying to kind of just see if there is a correlation between music and morality, and we were surprised to find some interesting relationship between actual music and morality or moral values. But as I said, there is no right or wrong in this model.
Okay, thank you. So, any other questions from audiences? Okay, so another question from me. So actually, I'm not sure about the generalist and specialist score. So could you explain again what it is and why you used that?
Yeah. So basically, generalist and specialist score is a musical feature that measures the diversity of music genre preferences. So basically, it is a vector representation of each music genres. So basically, people who are classified as generalist, they have genre vectors spread out in the space, whereas people who are classified as specialists have genre vectors more gathered or clustered together, closer to each other. And that's why, and what this exact score does, it calculates the cosine similarity between a genre vector and the rest of other genre vectors. So as if the GC score or generalist specialist score is high, this means the similarity is high for a particular user. Whereas if generalist specialist score is low, that means that we are dealing with a user whose diversity of music is quite big, and they have genre vectors spread out on this on the space, and that's why the similarity is low.
Okay, thank you. Okay, so any other questions? No questions? Okay, so thank you for the presentation. We will go to the next presentation. Thank you.
Thank you very much. Thank you very much.
Okay. So we will move to the next presentation. Okay, the title is Classification of 1950s to 1960 electronic music using the VGGish neural network and random forest. The presenter is Florian. Yes. Okay, please share your screen. Okay, if you are ready, please start.
All right, thank you, and hello. I hope you can see my screen, right? Yeah?
Yes, perfect.
Wonderful. Okay, just to explain, my colleague Maurício and I will share this presentation. So I will start off by giving some context and explain what was the background of our undertaking. So basically, we are dealing with the field of electronic music, which is a topic where we do find a basic problem in systematizing it. I will go into this question. We believe that there's basically a problem due to shortage of terminology, and this, of course, then holds true for electronic music, for the whole genre, but in specific also for the analysis of electronic music, which is the topic that we are taking into focus. There have been a few attempts to present universally valid tools, but there's still a lot of work to be done. And for this, we started to do some groundwork with the scientific project called Preset. We were allowed to present the basic outline of the project at the CMMR in 2019. And I may just quickly summarize what the mission of this project is. So we basically do a survey of studios for electronic music, and we visit many studios, as many as we can, to collect data. Data meaning, for example, equipment lists over time, lists of staff, and like anything we can find concerning actual working strategies in electronic studios, thus getting to know more about the basic underlying structures of composition and of music structure. The information we find is collated in a database, and we took the time to create a database that suits our project the best. It's a semantic web database with an ontology, a data ontology as underlying structural foundation. Sorry. I will just show you the basic structure of this database. It's called EMON, Electronic Music Ontology. So this is one overview of the whole ontology, that will just show you that we created a structure that allows us to connect data we find in the studio, and that is of course also connected to the existing ontologies, such as the music ontology, the device ontology, the connectivity ontology, and so forth. But this is just to show you the background. I will turn to the actual undertaking that we want to present here. As many of you probably know, there's a classic, if you want to call it like that, opposition of aesthetics of two early genres of electronic music. Of course, I'm talking about the Musik concrète and the so-called elektronische Musik that took place, or that originated around 1950. Just to basically sketch what we're talking about, we have the Musik concrète originating from Paris. I'm writing GRM here. I do know that the name GRM, Groupe de Recherche Musicale, was started existing in 1958. But let me just refer to this working context, to the studio as GRM, as well as just making this brief points. So Musique Concrète was an empirical approach, you could say, and it was mainly, or was centered around the strategy of manipulation of recorded sound. Whereas the elektronische Musik from the studio of the West German radio, or in the beginning the Northwest German radio, hence WDR or NWDR, originating around the same time, a little later, as many of you probably know, was rather constructing sound by means of recording technology. And this idea of constructing sound, like actually synthesizing sound, was following formally organized parameters. So what this means, this is of course linked to composition strategies that were connected with serial composing, as was a very important point, or an important direction of compositional theory in the 1950s. So we have these two subgenres, if you will, and we had the idea to take those debated aesthetical differences to an empirical test. What we wanted to check was, of course, a possible usability for future analysis tasks of what we're doing. And so what is the idea? We are going to analyze the so-called output of the two studios. And this means we purely base this analysis on acoustic features. So this means we are taking finished pieces, like finished compositions that were done in those studios as our input material of the analysis. We selected the data, and the first and probably most important selection criterion was that we would only use pieces from between 1950 and 1960. This is because in this decade, this whole debate I was trying to sketch was the most was most vividly performed, and so in this time, which is a typical kind of phenomenon that you have at the beginning of a genre, you will have a very strong you will have very strong points to be made, and also to try. You will have lots of debate and discussion. So after 1960, this whole debate would kind of lose energy a little. So we thought it would be interesting to compare pieces from the time when this was really the strongest opposition. Purely electronic means, of course, that we only would analyze recordings or electronic material, taking into account, of course, that the Musique Concrète uses recorded material as well, but electronic means like studio pieces and not recordings of pieces that combine instrumental and electronic or studio music. And as well, we excluded functional music because in both studios there were a couple of pieces made that were considered to be music for radio pieces or film music, which we believe would be a bias that would distract from the actual question. Our resource of information was the EMDoku, a freely accessible database under emdoku.de, provided by Volkmar Hein that is a very reliable resource to present you with lists. So the resource of information on the actual studio output that was potentially available was taken from this list. What we got, so we tried to retrieve as much audio material as possible. Of course, we couldn't get hold of everything, but we got 9.5 hours of audio material in total. From the West German radio studio, we got 3.5 hours of material comprising 57 items, meaning pieces or recordings. And from the GRM, it was a little more. It was 6 hours of material, 94 items. So this was where we, as far as we got, getting our basic material together. And the next steps would be to feed the data we collated into a deep neural network, and then try the DNN to try to train the DNN to identify difference between the two genres, as to test whether it could kind of tell these two opposed aesthetical views also in the acoustic reality, or in the reality of the acoustic results. And at this point, I will hand over to my colleague, Maurício.
Hi, everyone. Do I have a camera? Yeah. Okay, so basically, as Florian said, we narrowed down to this very specific kind of data. And so the idea is to do an initial experiment, this initial experiment just to test if some system or some architecture will be able to identify the difference in the acoustic features between these two subgenres. And so if we are able to do this, maybe we could use some sort of classification system to help identify some specificities in the material that we use to build this database. So the approach we used for this experiment, let me put, is to just use the VGGish neural network to compute embeddings. And then I will explain this in just a second. And then we use the random forest classifier to classify the embeddings, and then try to get what are the classes of each embedding. So the basic idea is to use this pre-trained deep neural network architecture, which is the VGGish. It's based on the VGG model, which is very well known for image analysis. And basically it gets the Mauch spectrogram from an audio source. And this is a mono audio file, which gets transformed into its time frequency representation. So some signals that we have are stereo, some have 4 channels. So we had to collapse everything in mono to be able to use this architecture. So there is some information related to this aesthetic that is lost this way, because this is part of the aesthetic or the genre, and having some spatial cues, spatial information, but it seems to work well this way. And maybe in future experiments, we may try using multiple channels. And so basically the audio material is transformed this way to Mauch spectrogram, and the Mauch spectrogram is divided into approximately 1 second segments, and each segment is fed into the neural network who generates embeddings for each piece. So this way we have 128 samples of embeddings for each segment, which is then classified using the random forest. So the random forest is just an ensemble of decision trees, which is trained to try to classify according to the class that we assign it. And basically, to assign a final prediction for each musical piece, we use the majority vote. And this way we can also see how much is the percentage of each class that each piece had. And to train the random forest, we use the data split in 70-30 to train and test. And we did a split in musical pieces in such a way that we avoid having embeddings from same song in both train and test sets. So the test set is clear from, so the system will never be tested with material that was used for training. And the same procedure was repeated 10 times, and the results are average in the end. And then for the performance metrics, each piece is accounts for one estimation for the performance. So the overall results have the accuracy of 82%, precision 89, recall 66, and F measure 0.74, which is reasonably good, not outstanding, but just to prove our point that some sort of automatic classification system could be used for to help building this database. It seems to be reasonable. And this histogram shows the distribution of percentage of correct classification within each class. So we have in green, we have the GRM, and in bluish purple, I don't know, we have the WDR class. And we see that the classification seems to be easier with the GRM class, whereas for the WDR, it seems to have a bit of a trouble trying to classify it. It's a bit more distributed on the percentage of correctly classified embeddings. But just to conclude our work, this classification experiment with musical pieces from the 50s, the results indicate that maybe this approach can be useful to help building this database and maybe helping identify in the future some specific equipment, some specific composer or technique applied. And this approach just considers CNNs, which don't take into account longer term temporal dimension. So this could be added as well and experiment with like LSTMs or transformers, some more refined technique that could encompass this kind of temporal dimension. But it's interesting that this material is it's a bit hard to identify in a musicological way because it doesn't have the common structure that we see in music. So we cannot extract some things like tempo or key or whatever. So it's an analysis much more focused on timbre and acoustic features than musicological features. Okay, so that's it. Thank you very much.
Okay, thank you for your presentation. So we move to the Q&A session. So if you have a question, please raise your hand or write your question in the chat box. Okay, so Tojo Sensei, please.
Okay, thank you. Thank you for the interesting talk. And I'm not very sure of the difference of the French school and the German school, but my understanding is that music concrete means they try to include every kind of sounds that can happen in the real world. Instead, that the German school says that is electronic means a kind of a artificial rectangular wave, for example. So why don't you try to distinguish what is the source of the sound in two schools?
So can I ask again your last sentence? I didn't quite get.
Yeah, you have to distinguish that is electronic music and music concrete. That is my understanding may be wrong, but is I thought that this is a simple difference of the source of the sound. That is
well, yeah, but of course, I mean, the source doesn't make the whole piece, right? So you would have lots of processes within the studio that will, of course, also give some stamp on the final result, right? So and the use of tape machines, for example, will also have its consequences on the final result. So I do think it does make sense, as well as the results from the studio in Cologne are not pure. Not only, I mean, there's like very pure or radical concepts like the very early sine wave pieces, but if you look into the later 50s, you will have pieces that are much more complex and will even contain recorded sounds like Gesang der Jünglinge, for example. So this is also where the whole discussion kind of merges into different directions again. So it's not, of course, it wasn't all that clear, but also, yeah, that, I mean, this was the basic motivation for us to see if there was an actual point to be made on the actual acoustic surface.
Okay, thank you. May I add one more question? That is I think you're talking about some music as a fine arts, like Olivier Messiaen, Pierre Boulez, Stockhausen, and so on. But later, the music concrete is applied to the popular music, like Beatles' Revolution No. 9 or Pink Floyd. And you are talking both, that is music as a fine arts and popular music.
Well, yeah, but musique concrète also, well, yeah, I think that is disputable. Of course, also, I mean, Stockhausen, for example, has also been quoted as an inspiration, also being printed on the Sgt. Pepper cover, if if you take that as an example. But yeah, I think that doesn't weaken our point to any rate. Or was that your argument? I'm sorry, maybe I didn't quite get it.
My question is you are treating both of the popular music as music concrete as a popular music and as a fine arts, as an epigone of the classical music.
Yeah.
Okay.
Yes.
Okay. Thank you.
Okay.
That's it for my question.
Thank you.
Okay. Any other questions? Kitahara-san, do you have a question?
Hi. So I'm not an expert over electronic music. So for me, so it's not easy to imagine the difference of these types of music. So can I listen to some example?
You mean right now?
Yeah. Okay, no.
This is going to be a bit difficult, of course. We were discussing before whether we should give some examples, but I think it's very difficult to just boil things down to super short examples, because there's of course quite a bit more of content and ideas related to it. But if you want, I can post some links to some pieces.
Good.
Maybe just I can check if there's anything to be found on YouTube that could be interesting to you. If that is a proposal.
Okay, good. Thank you so much.
But don't. I mean, it's just. I can just post something as a starting point. I wouldn't say that what I'm gonna be posting is like a full explanation of each genre, right? Just as a disclaimer.
And so I'm sorry if you already mentioned, but what is the biggest? What is the most characteristic difference of between the 50 and yeah.
Well, maybe I can just quickly try to explain. The Musik konkret is centered around the idea of working on recorded material. They started off with records they cut, and they used very simple methods of editing, like building loops, playing backwards, or changing the speed and pitch, and developing sound out of that manipulation idea. And also, like Pierre Schaeffer was one of the main forces in the beginning. This was connected also to the empirical idea of a new way of listening. So Musik konkret was basically, or in its very underlying structure, reflecting the medium it was produced on. Whereas the elektronische Musik from Cologne or Germany was rather connected to the serialist composers. So it was kind of a constructivist idea of parametrizing. No, can you say that? No, of viewing any musical parameter as something to be completely composed. So the idea of composing timbre, but with a formalized view in the background. Does that explain?
Okay, thank you very much.
Okay, so I will include in the chat just a few links if you like, but it's just going to be a little bit of illustration. So
okay, thank you. Okay.
Not going to cover the whole topic. Okay.
Yeah.
Okay, any other questions? Okay, one question for me. Okay, so I think the problem setting you tackled in this research is very similar to genre classification. So why don't you try compare with the conventional genre classification method or genre classification models to your proposed method, and why don't you try to use a transfer learning from such kind of conventional genre classification models into your
Yes, this was the first idea, but theoretically this could work. But we think that we have so little data, and the characteristics of the material is very different from popular music, Western music, because structurally it's very different. And we thought that maybe the best approach, or maybe the best initial approach, would be to tackle this problem using architectures that are more used in general sound classification, general scene analysis or whatever. So much more focused on timbre and specific characteristics of the sound in short term, instead of using systems that are much more tailored to identify things like tempo and key and some more musical features like this. But it's worth trying. Everything's worth trying, of course. Yes.
Yes. Okay, I understand. Thank you. Okay, it's almost time is coming. So thank you for your presentation.
Thank you very much.
Okay, we will move to the next presentation. Okay, the title of the presentation is Knowledge Transfer from Neural Networks for Speech Music Classification. And the presenter is Christian Kehling.
Yeah, hi everyone. I hope everybody can hear me.
Yes.
Perfect. So we'll just start sharing my slides. Oops. Oh. Okay. So welcome everybody. I just have to go back to start, and then we can start with the, my short talk about the knowledge transfer from neural networks for speech music classification. So this is my outline. I will also show this at the top of each slide so you can follow up. So when we start in the field of research, I think it's a goal of many fields to automate some processes and also to automatically retrieve information from different data. So the main aspect to do this is to eliminate the manual tagging from big libraries, because this often is error prone and also pretty much time consuming. So in the field of music information retrieval, it's also part to extract higher semantic values out of audio data. And one prominent part for this is also the speech music classification. So this can be used for like filtering big libraries, or also to monitor radio broadcasts to see if someone is speaking or actual music is playing. In the recent years, there are pretty good results in this field of research, also with the introduction of neural networks. But when working with neural networks, we also have to see that they commonly need a lot of training data to work pretty well. And also the actual annotated data for this is pretty rare. And the labeling that has to be done manually in this, especially for supervised learning, is also pretty expensive. And another fact is that we turn into new domains, like we have different recording conditions or other content. It almost always needs adaptation. So a possible solution for that is the knowledge transfer from data-rich scenarios, which is also called transfer learning. And in our work, we investigated like 3 neural network architectures that were initially trained on speech music classification. And subsequently, they were transferred, or the knowledge of them were transferred to new so-called downstream tasks to see if they also gain some knowledge in the training process, and this can be applied to. So the actual research questions were initially, how do these 3 networks perform on the initial training data, the speech music data? And the second one, if some of the knowledge that they gained during the training process can be transferred to new tasks, and also how close has these tasks to be to show some kind of knowledge transfer. So are closer tasks having a higher performance gain because of the knowledge that is transferred or not? So the 3 architectures that we focused on were first the INA architecture. It's from the Institut National l'Acoustique, and it was introduced first in 2018 at the MIREX Speech and Music Detection Challenge. It's a CNN architecture, so convolutional neural networks, and the input are some MFCCs, which were also mentioned before. The second network is a VGG-like network. You can also call it VGGish. This has also been mentioned by the talkers which presented before, and it's also a simple 2D convolutional network, and in this case with a logarithmic Mauch spectrogram input. So the last one we used is the SwissNet architecture. It was, I think, from 2019 and was more created in a lightweight way to get some fast computation and to do also a simple classification on speech music. And it's based on 1D convolutional network and also has MFCCs. So for a baseline, we also used two additional networks. On one side, we used the OpenL3 embeddings. They already achieved pretty much or pretty good results in the past years for different classification tasks in the audio domain. And they were created on a multi-modal way. So the input was audio and video content, as you can see below in the picture. And this was fusioned, and then the actual task was to say if the audio and video belongs together or not. And this kind of training is also a self-supervised fashion, which has some advantages because there's no labeling needed. The data is created by itself. And we also have, like, in theory, actually limitless data. The second baseline is a simple DNN baseline, just just consisting out of an input of 128 Mauch spectrogram, followed by one dense layer and then the actual classifier. So the data sets that I used, or that we used for this, were on one side for the training, a combined data set of, actually 4 other data sets. So the Musan and the GTSAN speech music data set are pretty well known in the area of speech music detection. And in addition to that, I used one data set from Matthias from 2019, and another one which is called the ACMUS YouTube data set. And these 2 data sets also include, like, non-Western music, so traditional music from Slovenia or Colombia, and also speech from these areas. For the actual transfer, I used some other data sets. So in the first point, the Slaney and Shira data set, which is also a speech music classification data set. And in addition, the ACMUS MIR data set. And there I used, like, 2 subsets. One is the instrumental format set. And I used this for the actual task of ensemble size classification. And the other one is the vocal format subset. And I use this for 2 other classification tasks. One is female singer classification. And the other one is the accompaniment detection or classification. So to the actual method. So as I mentioned before, the main idea of transfer learning is to use the knowledge that we gained by the training of an initial network with a big data set where we have lots of data accessible. And then we use this knowledge and transfer it to another task or also another data set. And what we actually transfer are kinds of like the dimension of the network, the weights, which are getting fixed or frozen, and the parameters of the network. So when we take a look at the pipeline, we start by training the initial data set. Then we take or we freeze the model that we were training. We transfer it to the new task. And before doing some kind of retraining, we like cut off the final layers, which we also call the classifier. It can be the last layer or also some more. And then we only retrain the final classifier with like kind of less data or also for less epochs, and maybe hope to get good results because the preceding network already has some kind of good training before. An optional step that you can also be part of this is that you can like also fine-tune the preceding layers, which were fixed initially, so you can make them trainable again and see if this helps to push the performance of the whole network in the end. So this is also that we did here in our work, and here are the freezing strategies that we used. So we started off with the normal frozen networks, which is pointed out with the red line. So we only fine-tuned or trained on the new tasks the final classifier in the end. But afterwards, we also tried some intermediate fine-tuning. You can see this with the green line. So we unfroze or make trainable some of the last layers again to see if this helps us to get a better performance out of the network. And the third strategy is to just like make the complete network trainable again and see if this works and use only the pre-training as an initialization for the network training for the new tasks. So from the workflow, just to make it clear, we trained on speech music data, then we transferred the model to the new data, adapt the classifier, and then go on the different fine-tuning strategies. And then we compared this with actual, the same three networks which were trained on the new tasks, but from scratch. And then we can see if maybe the fine-tuned or the trained networks which were initialized with the speech music training before, if they gain a higher learning effect. So if this is the case, it would be good. And we can see that something has been learned from the speech music training before. Now you can see here the actual results. So at first, the initial performance of the networks that were trained or in the training phase. So we can see that at least the three networks that we investigated, so the VGGish, the SwishNet, and the ENA, performed almost comparable. And I also included in the comparison an alternative input representation, so the MFCC and the MEL-spec for most of the networks, just to see if we change from MFCC to MEL-spec if there's any performance drop. But in most cases, it was actually not the case. So it seems that the MEL-spec is also working slightly better. So for the future experiments, I just eliminated the MFCC representation, and for the sake of comparability, I just kept on working with the MEL spectrogram representation. And you can also see that the OpenL3s that I included as a baseline here work remarkably well on the speech music classification and are also pretty robust for that. So for the transfer tasks, I created this kind of big table. And just for the explanation, so we have 3 columns with results here. In the first column, I present only the fully frozen network, so where only the classifier was trainable. This, the 4th column is dedicated to the intermediate state for training. And the last column comes to the networks which were completely trainable again. So as OpenL3 has always been completely frozen, we just used the fixed embeddings and only applied the final classifier. It was always mentioned in this 3rd column. And the DNN baseline was always completely trainable. So I mentioned it in the last column where we have the completely trainable architectures. The last thing to explain is that we always have the difference between the embeddings. So it's for each network, we have these AMP underscore thing. And also we have the origin, or the original. And the original means nothing else that this is the same network, but trained for the new task from scratch. So I also put this in this fully trainable area. Now we can take a look at the actual single class or single tasks. So the first task was actually just a data set transfer. They kept the task the same, so it was also the speech music classification. And obviously it's visible that here some kind of learning has been has taken place. So compared to the actual architectures that were trained from scratch, the fixed embeddings are working kind of better, especially for the ENA and VGG like models. So it also works better than the plain DNN baseline, which indicates that there has some learning taking place. Nevertheless, OpenL3 remains best with its 99% performance. Another task, which has also kind of a close relation, is the accompaniment detection. So meaning that we take a look if there's accompaniment in the music or not. The data set consists of vocal only parts, but also parts with instrumental accompaniment. So, and here we can see that the actual learning effect is disappearing, because when we take a look at the original networks from each network or from each model, we can see that the values tend to be higher than the embedding values that are here or all over the different freezing strategies. Also, the plain DNN has a pretty better result than the actual embedding, so there is no learning effect that can be achieved here. When we take a look at tasks that has some kind of a weaker relation, so actually in the first task we focus more on the voice, in the second task more on the instrumental part of the music. So first of all, we have the male-female singer classification. We can also see here that only the ENA network is some kind of profiting from the pre-training, so that the embeddings work slightly better than trained from scratch. But for the other networks, there's no real learning effect visible. And also we can see here that, nevertheless, we can see that the SwishNet embeddings on their fully trainable phase achieve the highest performance in this task. But as I said, there's no clear learning effect in that case. So the other task was the ensemble size tasks, or the ensemble size classification task. Here we have 5 classes, which said if there were 1 instrument playing, 2 instruments playing, up to 5 or more. And we can see that the actual accuracy tends around 50%, but is also always worse than their counterpart that was trained from scratch, and also the baseline from the DNN network. Here also we can see that OpenL3 is the best one with like 76% accuracy. So the last thing that we checked was the different freezing strategies. It's a little bit, it's much to have a focus on, but the general outcome of this is that with more degrees of freedom, all networks tend to increase their performance. But this is also really task dependent and also network dependent. So the SwishNet benefits in this case most of the grades of freedom. So the fully trainable networks are always the best, or in most cases the best for SwishNet. On the other hand, the ENA becomes more unstable when you give them more degrees of freedom, and it tends to fluctuate more. And the VGG-like, has its best values mainly in the intermediate state. So to conclude, we can say that we have investigated these 3 architectures, the ENA, the VGG-like, and the SwishNet, and they performed really comparable on the initial training task of speech music classification. Another thing is that the pre-training only is really beneficial when the task is pretty close, or even the same task. So just by shifting the data set, it would be good to do some kind of this pre-training. So for other transfer tasks, we cannot really significantly observe a learning effect in this case. We can also say that we can not see any big difference of a close or a more unrelated close relation or a weak relation, so to say. So there's no clear evidence that this is helpful in some kind of way. But what we can see, obviously, is that the OpenL3 embeddings are work best in most of the cases which is so to see the most unrelated embedding that we used for this comparison, and it outperforms in many tasks all the other networks. So a possible cause of this could be the nature of its training. So these self-supervised training with this with its limited data, unlimited data, might be a real good cause that it performs so well and also pretty much robust. So here are just some references that I used for the talk, and at least I want to thank you for your attention, and I'm open for questions now. Thank you.
Yes, thank you for your presentation. So we will move to Q&A session. So if you have a question, please raise your hand, or please write your question into a chat box.
I will just stop my sharing, right?
Yes.
Okay.
Okay. So okay, please Enrico.
Okay, hi. Thank you for your presentation. It's very nice one. It's just a very practical question. I remember that OpenL3 gives you the option of choose from different dimensions of embeddings. And which dimension did you use?
Yeah, we so we focused on like the one fixed configuration, and it's you have like the 512 embedding vector that you can choose from, and also a pretty big one, which was like 6,144, stuff like that. So we took the small one because the other ones are really time consuming to calculate. And then you also have the option to choose between environmental configuration and music configuration. And we also focused on the music configuration with the 256 bell spectrum input. Yeah. Okay,
and there is a huge difference between the dimensionality of the embeddings from different architectures, right? The VGGish is much smaller from the OpenL3. Yes. Okay. Thank you.
It might be worth mentioning that we also used, like, for the OpenL3 embeddings, the same classifier in the end as these plain DNN that I talked about. So 128 dense layer followed by the actual classification layer.
And did you experiment? I think you said no, but did you experiment with the environmental configuration? Because I remember that in their paper they mentioned that maybe good results can come even from not matching the actual configuration for the downstream architecture, or what the type of material that you're analyzing.
So we did this, but not for this work. So we did this for a subsequent work that we presented at the UZIPCO last year. And there we just saw that the environmental classification is almost always a little bit underneath of the music. So there's no big difference, but for different class, we had also the ensemble size was in it and also the speech music stuff. And music always tends to be best.
Okay, thank you.
Yeah.
Okay. Any other questions? Okay, so question from me. So you tried 3 types of network architecture. So and the experimental results shows some differences between the network architectures. And for example, why such kind of differences? Why the network architecture makes differences? How do you think? What do you think?
So the question is, are they why they are not different, or?
Not different, or for example, For example, the network of about the SwitchNet. So the transfer learning makes improvement of the performance, slightly improvement. Improve the performance. For example, speech music classification. About the speech music classification, the performance improves from 92.3 to 95.0. But however, the other two networks, the performance decreases by using the transfer learning. So why that kind of differences?
We might have a quick look again at the results so that everybody can follow. I just like share the slides again.
Yes, please.
So for the speech music task, we can see this here. We have the SwitchNet embeddings, which were in the beginning. So if they are fully frozen, there's no big improvement to just train them from scratch, right?
Yes.
We can see that here almost the same performance. They only tend to be better when we have more degrees of freedom. So we did the intermediate freeze or the fully trainable network. I don't actually know why this might happen. I mean, the network is like with its 1D convolutions has a slight other design and with its skip connections. So it might be a possible part that it's just because of the actually design of the network that it's not learning that well. But the other twos are just performing better. So there we can see that something's happening. Yeah. Also, I think, no, I don't know. So the input representation is also here, the MEL spectrogram. So it's the same for all of the networks. So it might really be caused that the convolution is just getting one way. And maybe this is not really good for learning the features for this task or gaining knowledge in that way. This might be a possible thing.
Okay, thank you. So I'm sorry. So the time is exceeded for this presentation for us. So thank you for the presentation.
Thank you.
Okay, we will go to next presentation. The title is 3-level model for fingering decision of string instruments. And the presenter is again Hori.
Yeah, thank you very much. And can I share my screen?
Yes, please.
Okay, I'd like to talk about a 3-level model for fingering decision of string instruments. My name is Ken Hori from Asia University. And string instruments have overlaps in pitch ranges of their strings. So therefore, string instruments have several ways to play even a single note. So that's why there are numerous ways to play a one song. And that's why the fingering decision for a given song is not an easy task, especially for beginner strings players. And that's why several researchers are attracted to develop automatic fingering decision mechanisms. And guitar scores for beginners are usually attached with tablatures. Tablature is something like this. And as we will see later, the tablature gives the information of string assignments for each note. And actually, it doesn't give total information of left-hand forms. But from the tablatures, human guitarists can easily estimate the finger assignment for constructed left-hand form. And some researchers have applied HMM, hidden Markov model, for fingering decision. So where the hidden states are left-hand forms, and output simples are notes, musical notes. So if we are given a sequence of musical notes, then we can estimate the sequence of left-hand forms using this hidden Markov model. So in this talk we don't go details such as transition probabilities or output probabilities of the hidden Markov model. But if you are interested in such details, please look at the paper and references therein. So in this formulation, fingering decision is cast as a decoding problem, HMM. So in this formulation, the fingering decision is solved efficiently using Vitabi algorithm. And several Japanese researchers have applied HMM for fingering decision of such these instruments. So we applied HMM to guitar fingering decision, and Nagata Sako and Kitamura applied HMM to fingering decision violin, and Nakamura, Ono, and Sagayama applied HMM to piano fingering decision. And this is the main point of talk today. And so we note the difference between string instruments and other instruments in fingering decision. So comparing the fingering decision, guitar and piano, for example, so guitar fingering decision is much more complicated. So although we call it just fingering decision, the problem consists of string assignment followed by finger assignment. So comparing to guitar, so fingering decision for piano is just a matter of finger assignment. So because if we are given a single note on score in guitar, so it corresponds to several strings. So comparing to that, so in piano, if we are given a single note on score, it corresponds to one key on the keyboard. So this is the main difference between fingering decision of string instrument and other instruments. So basically, this is the problem specific to string instrument. So other instrument than string instrument. So basically, there is one way to play a single note. So actually, there are several exceptions, but this is basically specific to problem of string instruments. So we introduce three-level model to describe the problem specific to string instruments. The model consists of three levels, that is note level and tablature level and form level, and where n of qi denotes the MIDI note number of the note, and si, s sub I denotes the string number, and if s sub I denotes the fret number, and h sub I denotes the finger number. So note level contains the information of note number, and tablature level contains the information of string fret pair to play the note, and form level contains the information of left-hand form, that is triplet of string number, fret number, and finger number. And we look at the problem settings based on the three-level model. So the first one is fingering decision from score. This is most common setting for fingering decision problem, in which we estimate the optimal fingering, that is the sequence of left-hand form from score, that is a sequence of note. So in this setting, so note level is observed symbols and form level is the hidden states. The second one is finger decision from tablature. So in this problem, so we are given tablature and we estimate the optimal sequence of form from that. So basically human guitarist can play the song given the tablature, because from actually tablature includes only the information of string assignments, but human guitarist, for human guitarist, it is easy to estimate the sequence of left-hand forms if given the tablature. But actually, this is required for example, typical application for this setting is that difficulty level estimation from the tablature. So difficulty in this formulation, so difficulties are defined as the product of transition probability between forms. So to assess the difficulty of the song from the tablature, so we have to estimate the sequence of form. So typical application of second setting is the estimation of difficulty level from tablature. The third one is finger decision from score with finger numbers. So there are some guitar scores without tablature and with finger numbers attached to some key notes. For example, something like this. So this score is without tablature and it has some. So for some keynotes, it has a finger number. For example, this is one means index finger. And so from the third setting is that is the estimation of sequence of left-hand forms from such this kind of score, guitar score. So in these settings, we estimate the sequence of form left-hand forms from the information of notes and partial information from form level. So we did some simulation for the third kind of program settings. So in these examples, only the notes with red circles are given, and other finger numbers and string assignments are generated from the hidden Markov model. So comparing the upper left example and upper right example, so only difference is finger number previously given to the score. So first, upper left example has given the index finger to the first note, and the upper right example has is given the little finger to the first note. Then the only difference are finger numbers with red circle, but so resulting fingerings are totally different. And in the bottom left example and the bottom right example, the only last note is given finger number, and the other finger numbers are generated from HMM, and they are quite similar, but the fingering and string assignment are different. So finally, let me conclude. So we have pointed out the difference in fingering decision between string instruments and other instruments, and we have introduced a three-level model for fingering decision of string instruments to describe the structure of the problem, and we have given a clear perspective for looking at variation of problem settings in fingering decision string instruments. So that's it. Thank you.
Okay, thank you for your presentation. So we will move to the Q&A session. So please raise your hand if you have a question, or please write your question into the chat box. Okay, Christian, please.
Yes, hello. First of all, thank you for your talk. My question is, so have you the model or the method you created, have you applied this to any kind of data set so that you have like some numbers that you can say, so we have like 80% accuracy, or this is the right fingering for stuff like that, or is it just, don't you have any real ground truth for that? So how is this in your case?
Okay, to be honest, this is the research in the early phase. So, but actually, I can say that I have presented only the example of monophonic cases, but the results can easily be generalized to polyphonic cases. So I can say that, but I haven't done complete simulation. Yeah.
And maybe one follow-up question. So have you also found something in literature that you can use like neural network for this kind of fingering search?
Yeah, I don't know. But I have looked at literature that applied genetic algorithm to such problem. Yeah, but I have tried, but that is much slower than HMM. And I have not seen the neural network application to fingering decision. Yeah.
Okay, thank you.
Okay, so any other questions? Okay, Tojo sensei.
Oh yeah, this is just following the same question. That is, haven't you implemented any computer system? That is,
yeah.
Oh yes.
Yeah.
So the input is the score and the temperature, and the output is some fingering.
Yeah.
Correct. Okay. Yeah. Perhaps the same question. That is, we'd like to simply know the performance. That is, how good or how bad is the result.
Yeah.
If you have any comment for your result of the performance.
Yeah. The problem is that how to evaluate the result. Yeah, that is problem. So if our method reproduces some tablature, so do you have any suggestion for evaluation this kind of system? That is a problem.
I'm not very familiar with, but Sagama Sensei has studied a hidden Markov model, and he has always shown some way of the performance. So just simply compare his results. Of course, that you have suggested that is a difference of the instruments. He had experimented on the piano and violin, and your case is guitar that is new. I know that is a comparison is not so easy. Yeah, but some comparison methodology should be common.
Yeah, so actually we have written a single paper in 2030. In that paper, we have compared our result with the result of some commercial softwares, such as Guitar Pro or other, I don't remember. And we apply our method to some music, and we generated fingerings using Guitar Pro or some other softwares, and we compared result, and we conclude that our method is better, but the basically evaluation is difficult. And also the problem is data set with tablature so is very limited, and that is a problem. Yeah.
Okay.
Okay. Any other questions?
May I add something to this problem? Because I think I get your problem, because when your algorithm, so your hidden Markov model, is just proposing something, it is not the only ground truth, right? So you have multiple ways to finger something on the guitar, and you cannot say that this is the right way to play it. It's just like one way to play it. And I guess the only way that you might create some kind of ground truth is to let actual guitarists play some sheet music and just see how they are playing it. So that might be one way to generate some kind of a ground truth. And maybe they are all playing the same way and in the same fret position. This might be something, how you can generate like at least some ground truth sets that you can compare to, right?
Yeah, that's a problem. So given a single song, so different guitarists plays in a different way. So what is ground truth in that case?
Yeah, I would just say like maybe the mean of some guitarists that are playing the same piece. So maybe they are actually all playing in the same positions. This might be something. Just as a proposal.
Yeah, okay, thank you.
Right, could I ask a question?
Yes, okay.
Yeah, on the subject of ground truth and playability, I did some research a few years ago on composing tablature music. So the idea was to create a compositional model which created not staff notation, but actually created tablature. And we were interested in a very similar problem, because we would produce some tablature, but we didn't know how easy that tablature was to play for a real guitarist. We were hoping that was the case. So we did exactly what the previous speaker said, and we created some tablature and sent it to a professional guitarist to play, and just asked him to comment on how playable it felt, how easy it was, you know. So we sent him 5 pieces and asked him to score 1 to 5, how easy or how difficult this is to play. And he said, you know, oh, this measure is very difficult because I cannot reach here, but the rest is okay, and stuff like that. So it could be a good way of doing some small evaluations.
Okay, thank you. And you are talking about composition or tablature generation?
Yes, that's right.
So sorry, I couldn't get your point. So your question or comment is, what is your question?
Just a comment that I did exactly the things that the previous speaker suggested. So we did compose some tablature and send it to a professional guitarist, and he rated how easy the fingering was to play. And so it does work. It's not so difficult to do.
Yeah.
Maybe I'll send you a link to the paper.
Okay, thank you.
Can I comments as well?
Yes.
Yeah.
Do you have time? Okay. Maybe I don't have expertise in this field of research, but as a guitar player, maybe a suggestion would be, if you have a corpus of data that is used by actual musicians. Maybe you can use this as a ground truth, as a good way of using the fingering decisions. And although you have multiple choices from which you can choose from one score, maybe you can use this as a ground truth and use this to train your approach, just as an initial step, because you know that this is a more natural decision to make that musicians actually use.
Yeah.
I don't know if it makes sense, but
yeah, thank you.
Okay, so any other questions? Okay, the time is almost coming, so thank you for your presentation. Okay, so all the presentation of this session have been completed, so I would like to thank all the presenters, questioners, and audience. Thank you. So as announced at the beginning of this session, there will be a 20-minute discussion session. So if you are a presenter, please move to the breakout room corresponding to your presentation number. And if you are an audience member, so please move to the freely move to the breakout room of the presentation you want to be discuss. Okay, so thank you so much again to all the participants. Thank you.
Thank you.